properties. So we calculated with the spin polarized density functional theory. Total energy of this system in spin density functional theory is expressed in the functional of spin density. This is the difference between the R-spin and unspin spin values. The spin density determines the magnetic property of the system, such as magnetic moment and magnetic ordering. So spin density rho x equal to rho upspin minus rho downspin. Upspin is alpha and downspin is beta. And spin polarization we calculated with the magnitude of difference between the alpha and beta and summation of alpha and beta spin. So integrated spin density we calculated integrated spin density. We found that the integrated spin density is the total amount of spin density in given volume. A material with a large integrated spin density is more magnetic. So manganese dot gallium nitride is a promising material. It shows high spin density. This is the manganese dot gallium nitride, single manganese dot. So after a single calculation, we calculated with different percentage, 3.1%, 6.25%, single transmitter, double transmitter, and triple transmitter, dot gallium nitride. We found that this manganese has so high magnetic moments. Manganese of gallium nitride is a promising spin terminator. It is of high spin density as well as high spin polarization. So these are the integrated spin density value of three transition metals of gallium side or gallium vacancy, and this is the gallium side with n vacancies. So similar properties studied with manganese and the iron and manganese sides that shows the greater spin density values. These are the graphs of this law. Then we calculated the spin polarization value. That is spin polarization value is calculated with spin up dots and spin down dots values. The spin polarization calculated with the formula, first formula, that is the difference between the alpha and beta spin divided sum of spin polarization. So we found that this is the manganese side showing the -0.5 strong spin polarization candidate for application, spin turning application. Also we found that the three reaction methods substitute the gallium side with gallium vacancy and for the gallium side with n vacancy. Similar cases for that is here the vanadium and the chromium side, that is the n vacancy with gallium side adopting for more beta polarization. Beta polarization means the downspin is more compared to the upspin. These are the graphs of the three transition metals of the gallium side with n vacancy, and this is the gallium side with gallium vacancy and gallium side gallium nitride. This is the two-product system, that is one chromium to manganese and two chromium to manganese. We also found that the similar trending of magnetic moments. So the chromium 2 and manganese 2 co-doping of gallium nitride source has greater spin density about 18.1124, which is H0 by 2. This is spin polarization value. Moderate spin gas polarization system but weak spin selectivity than the electron. Then the magnetic properties. Magnetic property in atoms and subatoms, magnetic moments are primarily caused by two factors. One is spin and orbital motion of the electrons. And atoms contain unpaired electrons. To calculate the magnetic moments with the unpaired number of electrons, if n is the unpaired number of electrons, then the magnetic moment equal to n into n equals to Bohr magnetism. And if we have calculated if the for free relativistic electrons, the spin magnetic moment is given by mu is equal to E squared by 2mg. So the magnetic moment arises for the half-paired d orbitals of the transition metal or the existence of unpaired d electrons. So So we calculated this is how we calculated the values of magnetic moment. First we calculate the number of upstream and number of downstream. Then we calculated the ampere electrons by subtracting both. Then we calculate the magnetic moment in Joule per Pascal and with Bohr magnetic values. So after calculating, we calculated for all the constant metal W value related. We found that the manganese for single atom working, the manganese shows better magnetic moment. Then we calculated for the different concentration, 3.5%, 6.5%, and 25%. We calculated. So we found that the manganese protein shows better with the manganese at 9.35% with almost 15.968 Bohr magnetic. Then also for the vacancy calculation, we calculated from gallium side dot to the gallium vacancy, gallium side dot with the vacancy. So we found that the gallium side, 3 manganese of the gallium side dot with gallium vacancy, so the highest magnetic moment. And in the case of nitrogen vacancy and gallium side dot, we also found that the magnetic is the highest. So manganese dot with gallium and vacancy just to highest magnetic moment with 15 ampere electron. Most effective weapon for inducing strong paramagnetic wave. So scandium, titanium, gadolinium has 0 ampere electrons, as it also shown in the Gauss plot. For the steel arm, the steel arm is selective nature, so there is 0 magnetic moment, meaning they are non-magnetic. Mediate transition metals enhance the magnetism. These are for the core system. Core system. So machine learning approaches we use different models. So different models are linear regression, polynomial regression, and support vector regression, decision tree regression, random forest. Just iteratively we calculate. We are not the machine learning domain, but we tried with iteratively with the different course found in online, that is linear regression and polynomial regression. For these are the models we used. So these are the models we calculated, predicted, integrated, stream density value. This will be for the linear regression, this is for polynomial regression, support vector regression, this is for the regression. This is the random forest and neural network and regression, random regression. Then after this model, we tried with different models. We calculated the mean square error value and the R-square values, MSE and the R-square value. If we found the lower MSE and higher R-square value, it is the model will be best performing model. For according to this, we found that the MSE is 0 and R-square value is 1 for the linear regression. So the best number is linear regression. So the predicted integrated stream density value using reverse machine learning regression model were evaluated based on the two key parameters. One is mean square, another one is R-square. So the question is that is this model will apply to different atomic model, different compounds or different material. But we tried with our small database where it is not going to be for the all materials. So my work is existing work is we compare with the different existing work. So first my properties, then the existing method comparison and the properties. So for the DFT study, there are some studies there, also experimental studies there. But the systematic study of the spin polarization value and spin density value are lab there. So in the first cases, our understanding is the spin polarization behavior and 9.3% document time frequency and also magnetic properties. And the existing method also seeing some some properties of PV temperature they are calculated. which shows the 940. Okay, so it is also ferromagnetic mineral, and there is also one paper in mineral that is the chromium and manganese coating is there. So there they also found the ferromagnetic compound. We also found this stimulation, stabilization, high magnetic moment is there. Tandem doping, yes, semiconducting behavior, non-magnetic moment. We also found that tandem is semiconducting behavior. Sorry, non-magnetic moment is there. And titanium case also there. So these are the paper existing one which matches with our results. So we conclude that the manganese drop is good for the highest magnetic moments. It is the Bohr magnetism and maximum spin density making best index for this reason. Chromium doping with chromium and manganese before doping also shows the highest magnetic moment, also high integral spin density. Then medium tensor metals, chromium manganese ion shows promising magnetic behavior, and the observed magnetic behavior there. Tandem titanium Zn are non-magnetic dopants, and these earlier electrons, so they are unpaired electrons, leading to no spin polarization. And also found that the gallium state with vacancies enhances properties, introducing gallium and N vacancies with transition methodology increases spin polarization, and especially manganese drop system. Dose analysis validates the half-metallicity of manganese drop radium nitrate, spin recovered density plot, half strong accepting the Fermi energy level of the dose plot. We also see that. Then indicating potential behavior, which is the key feature of this spin device. Then Peters confirms that Mn 3D dominance. The projected instructions have confirmed that Mn 3D orbitals dominate electronic and magnetic characteristics near the Fermi level, with notable hybridization of N2P orbitals. Then substantial structural stability is observed in the geometry of formation and formation energy calculation. We found that they are stable. Band gap tailoring for doping, we calculated with the LDA, GGA and LDA plus U. We can tailoring the band gap level with doping. Then p-type entire semiconductor behavior we also studied. SPDFT effectively captures the magnetic planes with which quantify the spin density magnetic ordering, confirm the DFT's reliability in magnetic material model. Then we try to implement the maximizing, and we found that the linear regression model with high expert acknowledgements effectively predict integral spin density levels, and strong exchange splitting with Mn system exchange splitting in d orbital, especially Mn electron, in significant magnetic differences between spin up and spin down state. The formation of the indicates favorable doping conditions. Most of systems, particularly MM frequency, also low functionality, then feasibility, experimental efficiency. Electronic asymmetry leads to ferromagnetic asymmetry in loss and fields. Correlates with ferromagnetic behavior, which is a prerequisite of BMS. Transfer method doping offers tailored function, with transfer method of the gallium nitrate, we can found various properties, the electronic, magnetic, structural properties, so suitable in next generation electronic devices. So future was band LD plus U. So there is we tried with the two different LD and GGA, and we tried with the hybrid parameter. But there, Haber parameter LD plus U level. But there is also hybrid functional there. But the hybrid functional approximation is computationally cost. So we will try this incorporation of spin orbit coupling spin dynamics. We does not spin orbit coupling here. The defect in the complex configuration, we will try different complex configuration and temperature different dependent magnetic behavior. Then experimental realization and synthesis also recommended. High level machine learning models with data aggregation with large set of data will try in future. These are the references. These are my publications. And these are my conference presentations. This is the patent. And I would like to acknowledge and request gratitude to my supervisor, Dr. Polarization, for her continuous valuable and supportive assistance to every stage of my research. And sincere gratitude to Mr. Director Sir and Polarization and Sushant Sir for their providing necessary research with sincere thanks to all the faculty members of physics department and thanks to Antal Bhai and Mamlaki Madam for their advice and encouragement in research, and also give different gratitude to Sonia Sajat and all the program research for their encouragement and